Okay, welcome everyone to the Analyzing and Visualizing Interactions in R workshop. My name is Andy Lin, and I am the manager of the UCLA Statistical Methods and Data Analytics group. I'm here with several of the consultants in my group, including Katrina Kaite, Shars Divsalar, and Sivas Jalal. They'll be monitoring the chat, so if you have any questions, please go ahead and put them in the chat. The workshop is being recorded, as many of you probably just heard. We do hope to post this on our YouTube page at some point, but it will take a few months for us to edit it. And that's, of course, assuming that we like the recording that we get today. Okay, so if you're just arriving, there is a web page on our website associated with this workshop. I've linked that in the chat. On that web page, let me go ahead and start sharing screens. On that web page is a link to the slides right here. So if you click on this link, you'll get the slideshow popped up in your web browser. It is an HTML slideshow. It's not a PDF, but if you do want to save it, you can print it as a PDF, or you can save the workshop also by right-clicking on it and following these directions right here. But it's always here available on our website for you to look at. And it's pretty much self-contained in the sense that you should be able to look at it yourself, follow it yourself, without necessarily watching this live. But it was designed to be that way. Additionally, on this web page, I have a link to the code file. And if you don't have RStudio open already, why don't you go ahead and open it? If you plan to participate in the workshop, you don't have to, it's totally up to you. But if you want to participate, then please go ahead and open RStudio. And then if you click on the code file link, it opens up directly here. And one thing you can do is just copy the whole page, for example. You can highlight it if you want. It's pretty long. Or you can, on most computers, you could hit Control-A to select it all, and then copy it and paste it into the R script editor, right? And all the code that is in the workshop is available on that code page right here. You can also download it if you like by right-clicking it to download it. But you can, like I said, you can also just left-click it and then copy the whole thing and paste it into RStudio. So if you want to follow along with the code, that's how you can do it. Now, to the presentation, as I said, it's an HTML slideshow. But if you'd rather look at it as just one continuous page, you can hit the A key, and then it will become one long web. That's the A key on your computer. That toggles between slides and making it like a flat web page. You can also advance the slides by using the arrow keys, left and right, for example. You can also advance with a mouse click, but I'm gonna actually recommend that you take that off if you want to copy and paste code directly from the slideshow. So if you hit the K key, you'll get this little message that shows here that mouse click has been disabled. That means that now when I click, it will no longer advance the slide. And if I want to copy and paste things, it's a lot easier if you disable mouse click advance. So once again, that is the K key. Okay, I'm going to go ahead and disable it on mine. These slides have all of the code and a lot of the graphs and the output that are made in them. So you should be able to follow along just by watching the slides. Okay. And with that, I'm going to go ahead and start the workshop. I'm going to start though first with a poll. I want to see how familiar people are both with R and with linear regression. So this is an anonymous poll. So if you wouldn't mind, just go ahead and answer these two questions. How much have you used R in the past is the first question. Then the second question is, how comfortable are you interpreting a linear regression model? Okay, I'll give a couple more minutes. Not minutes, a few more seconds for people to respond. Okay, well, I'm glad to see that there's mostly people who are somewhat familiar or very familiar with R and somewhat or very familiar with linear regression. Um, this workshop, cannot teach everything about R and everything to do with linear regression. We're going to review some linear regression at the beginning, but it would be probably smoother for most of you if you knew some linear regression before coming to this. Okay, I'll try my best to explain all the R coding as well. Thank you for um, participating in that poll. That helps me out to figure out where everybody is. Okay, so let's start the workshop. I have renamed it from what it was named when you registered for it. Now it's called Analysis and Visualization of Interactions in R, but it's the same topic, I promise. Okay, let me. So this workshop is designed to teach you how to analyze and visualize interactions in regression models in R, both using the emmeans package. And if we have time, we'll discuss how to do the same things without the emmeans package, just using base R coding. Okay, so the topics we're going to discuss today is first, we're going to do a review of linear regression. It's important that you have some comfort in interpreting the coefficients of linear regression before we get to interactions. And so I want to make sure everybody's comfortable. We're going to discuss dummy variables for categorical predictors. So we're going to discuss how you model categorical predictors in regression models with dummy variables. And then we're going to discuss main effects models. And we're going to contrast that later with models with interactions, and you'll see why. Then we're going to introduce the emmeans package, which is used to estimate what's called estimated marginal means. And we'll talk about what those are, and then show how we can use the emmeans to both estimate effects of variables and to also visualize the effects of those variables. Finally, after that, we're then going to get to the models with the interactions. We're going to talk about why we want to model interactions, what's the point, and then how we model them with product terms, and then give a general guide on how to interpret the coefficients in models with interactions. Then comes the meaty part of this workshop, where we're going to use the emmeans package to analyze, interpret, and visualize two-way interactions first. And we're going to discuss both continuous and categorical variables involved in interactions. And we're going to briefly also touch on, if we have time, hopefully, interactions in generalized linear models like logistic regression. Then, time permitting, we're going to talk about analyzing and visualizing interactions yourself without the help of the emmeans package. And this might be useful if, for example, the regression model you're using isn't supported by the emmeans package. And to do that, you'll need to learn about estimating simple effects by recentering variables and resetting the reference group. And also then you'll need to learn how to do predictions and then graphing those predictions. And it may sound intimidating at this point, but I promise you it's really not that hard. And I'm sure anybody can pick it up. Okay. Okay. So again, if you have questions, it's okay to unmute if you like, but you can also, if you prefer, ask the question directly in chat. And although I'm kind of sometimes looking at chat, I won't be able to look at it all the time. One of the other people in my group should be able to answer the question for you in the chat as well. Okay, so let's get started with first discussing the packages you'll need. You're going to need the emmeans package and the ggplot2 package. I believe ggplot2 is a dependency of emmeans because all of the graphs it makes are made in the ggplot2 style. So if you install emmeans, it probably will install ggplot2 for you as well. Either way, you're going to need just those two packages for today's. And then throughout the workshop, we're going to be using this example data set. And it contains data that describes an experiment on mice being fed 3 different diets. And the outcome variable, or the dependent variable in this data set, is weight. So we're going to be measuring the weight of these mice on 3 different diets at different ages. And that's the second variable, age, which ranges from 2 to 16 weeks in increments of 2. Then we're going to have a diet variable. So this is one of our predictors. Well, all of these are predictors besides weight. And age is one predictor, diet is another predictor. And that is one of 3 diet types. So there's a high fat diet, a high starch diet, and a control diet. each mouse is only fed one of those 3 diets. And then we have the sex of the mouse, male or female, the litter size that the mouse was born in. So how many pups were in the litter that the mouse came from, and that ranges from 2 to 10. And then a binary variable called hyper, which describes whether the mouse was diagnosed with hypertension. Okay, these are not longitudinal data. Each mouse is measured exactly once to keep things very simple, so we don't have to do any kind of modeling of the dependencies of the observations. We're assuming all the observations are independent because each mouse is measured only once. I do want to stress that these data are artificial. I made up this data set myself, so please do not make any inferences about mouse weights from these data. I try to make it somewhat, ballpark realistic, but everything else you should not take as meaningful in the real world. Okay, but it's designed to be able to, instruct you on interactions. Okay, so that is the workshop data set. Now, we can assume they're all from different litters as well, so they're all completely independent. For the sake of this workshop, let's assume that they're completely independent in all ways. Okay, so we're going to review linear regression, and we're going to start with very simple models so that we don't get too complicated too quickly. And I want to be able to interpret the coefficient of a regression model first with a single continuous predictor. In general, a regression coefficient for a predictor will be interpreted as the expected change in the dependent variable for a unit change in the predictor, or for a 1 unit increase in the predictor. So here we have a regression model where the weight for mouse I is predicted by some intercept B0 plus age of the mouse times some coefficient relating age to weight. And then there's also an error term for the mouse, which allows the mice to vary around some mean weight. So this is kind of like the unexplained variation. We're not really going to be talking much about the error term in this workshop, so for all intents and purposes today, you can pretty much ignore them. But I put them in to be reflect what a real regression model would happen. Okay, so what we're really interested in today are the estimation of these coefficients, B0, and in particular, B age. So to run a linear regression in R, we're going to use the LM function. And then inside LM, you put the dependent variable first, then a tilde, and then the independent variables, which if there's more than one, you're going to separate them with pluses, as we'll see soon. Then we're going to save that into an object. And I'm going to refer to this object a lot as the model object. Okay, and then the model object basically contains all of the model results, and we can extract those results in different ways using these functions, like summary. So here we have summary used on the regression model object, and we'll get then this regression table, which includes the estimates of the coefficients and the associated standard errors and p-values and t-values, for example. So we want to be able to interpret these coefficients, even though emmeans is going to do a lot of this work for you. It's important that you be able to interpret your model, because if you ever need to present this model, you want to be able to talk about it in an informed way. So the first thing we'll interpret is the intercept, B0, this one here. So the intercept is the expected outcome when all of the predictors in the model are 0. Well, we only have one predictor here, and that's age. So this is the expected weight of a mouse at age 0, at birth, basically, at 0 weeks. So that is 19.86 grams. Then we have the coefficient for age. And this, again, is interpreted as the expected change in the outcome for a 1 unit increase in this predictor age. So for every additional week of time, we expect a mouse's weight to increase by 0.53 grams. Okay, all right. And again, if there's any questions, please go ahead and ask me, or you can put it in the chat and ask it. All right, so that's a continuous predictor. That should be pretty straightforward for most of you. We also can model categorical predictors in regression. And to do that, we use dummy or indicator variables. Oh, there's a question about the p-values. I'm not going to stress p-values too much today, but the p-value represents what is the probability of observing this t statistic, which is a function of the estimate divided by the standard error. What is the probability of this t statistic if, for example, there is no age effect? If the age effect is in fact 0, how likely are we to see this? And the question here is very, very unlikely. This is a very small value. The F statistic is just a test of the overall model, whether any of the regression coefficients are equal to 0. Here it's only testing one coefficient. Okay, so as I was saying, regression models, we use dummy variables to represent categorical variables. And in a dummy variable, we coded 0 to mean not belonging to the category. And then we coded 1 to mean belonging to that category. Okay, so a variable with k categories can be represented by k-1 dummy variables. So if you have 2 categories, you're actually only going to need 1 dummy variable to represent that categorical variable. So sex in our data set is one example of a categorical variable. And we have 2 sexes, so we'll only need 1 dummy variable. For example, I could create a dummy variable called female, which is 1 if they're female, belonging to the category, and 0 if they're not, right? And we know then if you're 1, you're a female, and if you're 0, the mouse is male. On the other hand, we also have a 3-level categorical variable, which is diet in the data set. And remember, the 3 levels are control, fat, and starch. High fat diet, high starch diet, control diet. So for a 3-level variable, we need 2 dummy variables. And it's your choice as to which dummies you want to create. Here, I've created a dummy variable for the fat diet and the high starch diet. And so if the mouse is fat, it'll be 1. If it's either starch or control, it'll be a 0 on that variable. And then there's another dummy variable representing starch, and it'll be 1 for starch, and then 0 for the other 2 groups. Okay, so in order to then code for control, you'll notice that control is 0 on both variables. So that's why we don't need a 3rd dummy variable, because the omitted group is implied by being a 0 on all of the other dummy variables. Okay, so when you're creating these dummies, you do have to pick which group you're going to omit. And in this case, for example, I omitted the control group. And when the omitted group is often referred to as the reference group in regression models. All right, and so henceforth, whatever group there is not a dummy variable representing in the regression model, I will call the reference group, and that'll be important. And yes, I do want to stress that we only have the capacity to answer questions that are relevant to the workshop. So please do keep your questions relevant directly to the workshop. If you have a question specifically, for example, about your own research that's not directly relevant, we probably won't be able to answer that. Okay. Okay. All right. So hopefully everybody has dummy variables, at least the idea of dummy variables down. If not, please ask questions. The way we're going to represent dummy variables in R is through factors because they make it easy for us. And factors in R are essentially integer variables with labels for each integer value. There's a function called factor that we can use to convert character variables or integer variables to a factor. Okay, so a character variable is something that has, letters in it. Then if you, after converting it to a factor using the factor function, if you want to look at the distinct categories of that factor variable, you use this levels function here, okay? So here I'm starting with just a vector of words, essentially. This is not related to the mouse data set, but here's a vector of words representing income, and I have low, mid, and high, right? I want to convert this to a factor. What I do is I put it inside factor, and then R will convert it to a factor. What that means, again, is that there will be integers underlying it, and then labels for those integers. So essentially, it will create a 1, 2, 3 variable with labels low, mid, and high. When I look at levels, using this levels function, it'll tell me what the distinct categories are of that factor. And here you can see it's high, low, mid. And levels outputs the levels in the order that it's stored in the factor. So high is the first group, which is coded 1, low is the second, coded 2, and mid is third, coded 3. In this case, you may not like this ordering, right? High, low, mid is not the most natural ordering of these three values. Probably we want low, mid, high, right? That's a more natural ordering. So if you want to specify them in the order of the levels in a certain order, you put those levels in order inside of this levels argument of factor. So here, instead of just putting income inside a factor like I did up here, instead I'm going to specify the levels low, mid, high inside of this levels argument. And I put them inside of the C function, which just combines things into a vector. So now it'll make low the first group, mid the second group, and high the third group. All right, so now you can see that when I use levels on this factor income variable, the order is low, mid, high, which is a more natural ordering, right? As I said, there are integers underlying this factor. We're actually never going to use them throughout this entire workshop, but I just want you to know that they're there. So if I convert this f income variable that I've made into a factor, if I convert it into a numeric variable using as.numeric, you'll see that the underlying values are 1, 2, 3, 3, 1, 2. So based on this, I know this is low, mid, high, high, low, mid, right? Low, mid, high, high, low, mid. Okay, but again, you're actually never going to really use these. It's just to know that, just so you know that they're there. Sometimes you may have your data set and it comes with a factor categorical variable already coded as integer. You know, somewhere else you may have the labels, but in the data set, they may already be coded as integers. If that's the case, you can still use factor directly on it, but now you'll need to use the labels argument to apply the labels to the factor, okay? And then these labels will become the levels themselves. So here I'm starting with a numeric version of income, which actually is coded 0, 1, 2 in this case. I want to make it a factor. R will naturally order them by their numeric ordering. So it'll go 0, 1, 2. So 0 will become low, 1 will become mid, and 2 will become high here. But as you see, when I use levels on this factor, it returns low, mid, high. So the levels now are actually low, mid, high. This numeric variable, if I just type it out to look at it, you can see that when I look at it, it prints out the levels now, not the numbers. All right, so you can only see the numbers if you use this as.numeric. Otherwise, you'll only see the labels. So why am I going through all this? The reason why is when you are using a regression model and you have a factor in there, R will create the dummy variables for you. You don't have to create dummy variables yourself and add them into your data set. And so it's usually worth the effort to making a categorical variable into a factor just for that reason. Additionally, the plotting functions that we use also tend to work better when categorical variables are factors. Okay, so we have two categorical variables in our data set. We have sex and diet. And so I'm going to go ahead and create them as factors or convert them into factors. So originally they're character variables that just say male or female or control fat and starch. And I specify these in order. Okay, so the first group of the factor is going to be the reference group in the regression model. So that's the default behavior of R, is to make the first group the reference group. So when you're making your factor, think about which group you want to be the reference group and specify that group first in levels. So my reference groups are going to be male and control. Then when I look at the structure of my data set, you can see now that sex has been converted to a factor with 2 levels and diet has been converted to a factor with 3 levels. Okay, that's factors. Hopefully some of you are already familiar with factors, but for those of you that aren't, I do recommend that you get familiar with them if you're going to be modeling categorical variables. Okay, so as we discussed, when you model categorical variables in regression, and if that categorical variable has k levels or k categories, you're going to enter k minus 1 dummy variables in there. Can't enter all the dummy variables in there with the intercept, because you'll have what we call perfect collinearity. Usually the program will actually throw one of the dummies out because it can't estimate. The dummy variable that's omitted from the model, again, is going to represent the reference group, and the coefficients in this regression model are going to represent differences from that reference group, okay? So, for example, here we have a model where weight of the mouse is now being predicted by diet. And we have an intercept, and since we have 3 diet levels, we're going to need 2 dummy variables. And I'm going to have R create dummies for the high fat group and a dummy for the high starch group just by creating a factor. Therefore, the control group is the reference, and then these coefficients for the fat and the starch groups are going to represent differences in weight from that reference group of control, okay? So it's very simple to specify the model. We're going to use LM again with weight, tilde, diet. Since diet is a factor, R will know to create dummies for everything but the first group and then enter them into the regression model. Then when I do a summary on the model object, again, the intercept is the expected or predicted weight for a mouse with 0 and all the predictors. Well, 0 on the fat dummy and 0 on the starch dummy, what does that mean? That means the control group, right? So the intercept is the estimate for the control group when you have dummy variables in the regression, all right? So this is the expected weight for a mouse on the control diet. Then these coefficients represent differences from that control reference group, right? So now we know that fat minus control is 4.01. So mice on the high fat diet are expected to weigh about 4 grams more than mice on the control diet. And mice on the starch diet are expected to weigh 3.45 grams more than mice on the control. Okay? Okay, so far, so good. Now, in each case, we've only really added 1 variable as a predictor, although this diet variable really consisted of 2 dummy. Now let's add several predictors at once. So we're going to run a model now where weight is predicted by diet, sex, and age. So remember, diet and sex are categorical, age is continuous. We're not going to do any interactions yet. And this model is going to be is often called a main effects model. And then a main effects model, the effects of the variables do not depend, on the levels of the other variables. So these diet effects do not depend on what age it is. And this age does not depend on what diet it is or what sex it is. Okay, so that's a main effects model. Remember that our reference groups for our categorical variables are males for the sex variable and control for the diet variable. Okay, so we run this model through LM as before. We're putting pluses now in between the independent variables. I'm going to use, by the way, the words independent variable and predictor pretty interchangeably. Sometimes I'll even use the word covariate. All mean the same thing. And I'll also use the words outcome and dependent variable interchangeably as well. Okay, so the intercept again is the expected outcome when all of the predictors are 0. So when this sex female dummy is 0, that means male. When these 2 diets are 0, that means control. And when age is 0, that means 0 weeks. So this is the expected weight for a male mouse on the control diet at 0 weeks. Okay. Then the difference between male mice and female mice is this coefficient. The difference between control mice and the mice on the high fat diet, are this coefficient, and then difference between starch and control is this. And this is still the expected increase in weight for an additional week of age. Okay, and since all of these are main effects, none of these effects change when we change the other variables in the model. That's going to be different when we get to interactions though. Okay, let me pause here. Are there any questions about linear regression interpretation? specifically the coefficients, especially. All right, if there's no questions, I'm going to keep going. And if you still have some, feel free to put them in the chat. Okay, we're going to stop and do an exercise now. So I know we've been talking about this mouse data set, but we're going to have two data sets we're going to be working with at once. The mouse data set is mostly going to see in the slides. There's another data set we're going to practice with, which is this auction data set. So in this data set, this describes how much participants are willing to bid. So the bid is going to be the outcome on items in a blind auction. And in a blind auction, basically everybody just bids once, and then that's it. And then the highest bid wins. All right, so in this case, there's only one bid per person. And they're gonna make that bid depending on the quality of the item, which is what it looks like to them. And that quality is a number between 0 and 5. How long it is before the auction is gonna end, which is a continuous variable from 2 to 9. So hours and quality are two continuous variables. And then we have two categorical variables, rarity and budget. And rarity is how hard is the item to find. And it's one of three categories, either common, rare, or unique. And then budget is how large is the participant's budget. And this is going to be categorized as small or large. Okay, so what I want you to do is, if you haven't already, go ahead and make sure you have all of the code in the code file loaded into R. So again, if you arrived late, on the workshop webpage, there's a link to the code file. Go ahead and copy the whole thing into your R script editor. Now the exercises are at the very, very bottom. Okay, and this line where you want to load the auction data set is right here. And then I rewrote the exercises directions right here. All right, so if you want to follow along and try the exercises, then go ahead and scroll down to around line 415 and run this line auction and then the read CSV. So that'll load the data set into the R session, right? And if you just want to look at it really fast, again, bid is the outcome in dollars. Then we have two continuous variables, hours and quality, and then two categorical variables, rarity and budget. Currently though, rarity and budget are character variables. So the first thing we want to do is convert them into factors. I'm going to do this exercise with you. And if you want to participate along with me, that's great. If you just want to watch, that's also great too. It's totally up to you. So the first task I want you to do is to convert rarity and budget to factors. Okay. So I'll do this with you and I'll try to type kind of slowly. So the first thing we're going to do is we're going to write over the original variables. So I'm going to do auction $ rarity. Okay, and I'll be sure to not go too fast, I hope. And if I am going too fast, please do let me know. And then I'm going to assign to that with the arrow factor. Right, we're going to use the factor function. The first argument is the character variable that we're trying to convert to a factor. So again, I'll type auction $ rarity. And then I need to specify the levels. And the levels I want to put in order: common, rare, unique. All right. So then I can say levels equals C, right? Equals, and then C is what you use to combine things into a vector. I want the order to be common, rare, and then unique. Okay. So again, auction rarity, factor, and auction $ rarity again. Levels equals C, and then common, rare, unique. Okay, go ahead and run that. And then the next one is for budget. We're going to do the same thing, auction $ budget. We're going to assign to that factor. We're going to type auction $ budget again. You can use tab keys too, right? When it brings up the little choice menus, you can select one of the choices and hit tab and it will kind of finish it for you. And then I'm going to say levels equals C, and then the order I want is small, then large. So in quotes, small, comma, large. Okay, so once again, auction $budget factor, and the first argument is the variable that we're transforming into a factor, and then the levels where we specify the actual levels. Okay, and then you can go ahead and run those both. Okay, so that's the first exercise. Then the second exercise is run a main effects linear regression modeling bid predicted by hours and rarity. Okay, so I'm just going to call this model M1. Okay, now remember, what is the function we use for linear regression? It's LM, right? LM. Okay, and then remember the formula for the regression is the dependent variables on the left. So we're going to put bid on the left, then a tilde, and then on the right-hand side of the tilde come the predictors. And I said hours and rarity. Okay, and then you should name the data set that their variables are in, which is data equals auction. Okay, so this is the model object. LM is the function. Bid is the dependent variable. Hours plus rarity are the independent variables. And then this is the data set. Okay, then we want you to interpret the coefficients. So we'll just put that inside a summary. Okay. And after running summary on M1, the model object, you'll get the coefficients. So this is the expected bid when all of the predictors are 0, right? So when at 0 hours of waiting, and for the reference group of rarity, which is common. So a common item at 0 hours of waiting, the expected bid is 9.6. For each additional hour of waiting, the bid is expected to go up by $1.2. And you can see that on average, rare items are bid higher than common by $11, and unique items are bid higher by $29, almost $30 compared to common items. And again, this is a completely artificial data set, so don't make any conclusions on auction bidding based on this data set. It's completely artificial as well. Okay, are there any questions on this first exercise? Just getting used to converting to factors and running a linear regression model and interpreting it. Okay, are there any questions? I saw one question, before I transformed the factors, no, they were actually character variables that with values like just character like this. But usually it's better to convert them to factor if you're going to use a linear regression. Okay. Okay. All right. I'm going to go then move on in the workshop. Okay. Now let's look at the emmeans package. So the emmeans package can, first it can compute what's called estimated marginal means. And these are predicted outcomes at specific values of predictors and then possibly averaged over other values of other predictors. So for example, if we can get the expected weight at each level of diet, but then maybe averaging over sex, for example. It can also compute contrast between these estimated marginal means. And so it can, take two, let's say the expected weight for the high fat diet group, the expected weight for the starch diet group, and then do a contrast between those two predicted outcomes. That contrast will basically represent some kind of diet effect. So these contrasts will be used later on when we have these interactions to estimate simple effects. It can also generate graphs of model estimates and predictions, including interactions. Okay, the procedure for estimating effects and contrasts will differ depending on whether the variable whose effects we seek is categorical or continuous. All right, so when we're talking about an interaction, we'll get to this more, you need to pick one of the variables in the interaction whose effects you're really interested in. And if that variable is categorical, we're going to use this procedure. First, we're going to use emmeans function to estimate the estimated marginal means across values of the predictors. This produces an object of class grid. And I don't know if many of you are familiar with the idea of classes in R, but certain functions only accept objects of certain classes. And for example, this contrast function will only work on an object that's created by emmeans, which has class grid. So the only reason I bring this up is because you need to have the right kind of object to supply the contrast. And that object is something that's created by the emmeans function. So first you use emmeans to create an object, then that object is the first argument to contrast. This contrast then can estimate these effects between your effects of your categorical predictors. Finally, there's going to be an emmip function, which we can use to graph the interaction. Okay. Then instead, if you're more interested in the effect of a continuous variable, I'm going to start referring to those as slopes, right? Continuous variable you can imagine as has a kind of a slope that represents its effect with the outcome. The procedure is a little bit different there. We're actually going to skip the emmeans step altogether. So we're not even going to do this first step if it's a continuous variable whose effects we know. We're going to use the emtrends function to estimate the slopes of that variable at different levels of other variables. And then we're again going to use emmip to graph the interaction. One of the great things about the emmeans package is how many regression models it supports from various packages. So there's a link on this slide that if you open it, it opens to one of the help pages for emmeans. And these are all the classes of objects. Usually the function has the same name as the class. So you can generally think of this as these are all the functions that are regression models usually that emmeans supports. So for example, we're going to be looking at GLM later on for our logistic regression. But for those of you, for example, that are doing mixed models with LMER or LME, it's here. If you're doing mice, a multiple imputation, even that is somewhat supported. I think I saw CoxPH for survival. So there are quite a few packages that are supported by emmeans, which is why we like it so much, because it can be difficult in R sometimes to find packages that work with all kinds of other packages. So this is one of those great ones that does. Okay. So as we discussed, if you're looking at the effects of a categorical variable, the first thing you're going to do is use the emmeans function to estimate what's called estimated marginal means. Okay, to do this with the emmeans function, the first argument is the model object, right? So first you're going to run your regression, for example, in LM, and then the object created by that is going to be the first argument to emmeans. Second argument is specs, and in specs you put the variables. When we get to interactions, you're going to put the variables involved in the interaction in specs. But in general, what happens with specs is that estimated marginal means are calculated across levels of the variables in specs. So if you put a factor variable in specs, it's going to calculate a predicted mean at each level of that factor. So if I put diet in there, it'll calculate it for each level of diet. If I put a numeric variable in there, emmeans is going to calculate it at the mean of that continuous variable. I can change that behavior with another argument called at here. We'll go over examples of that. If you don't put the variable that's in the model inside of specs, emmeans is going to average over that variable. Okay. And as I said, basically, when we get to an interaction model, we're going to be putting all the variables involved in that interaction inside of specs when we use emmeans. Okay. We can even use it though, even if we don't have an interaction. So for example, this is my main effects model that I had before, where I had weight regressed on diet, sex, and age. And so for now, I want to look at the diet effects. And remember before, when we looked at this main effects model, we got a comparison of fat to the control group and starch to the control group. What I don't get for free though, is a comparison between fat and starch, for example. Well, I can get that directly through emmeans eventually. But first, we're going to do the emmeans themselves. So I put the model object as the first argument, and then the variable over whose levels I want to calculate the EM means, right, inside specs. So for now, I'm just going to put diet in there. And then this is the predicted weight for a control mouse, for a high fat mouse, and for a high starch mouse, averaged over sex and at the mean age. Okay. That averaging is, it's not super important you understand it right at this moment, but just know that it's going to basically average over them. So if you want to know how it's calculated, for example, for the EMM for the control group, it's taking the intercept. Each of the regression coefficients gets a 0 for the diet groups. It's going to average over the females and males by putting a 0.5 here, and then it's going to estimate it at the average age, which is 9 weeks. So putting this all together, you get 22.2. It's not actually that important that you understand these calculations right now, because most of you are not interested so much in these EM means themselves. You're going to be more interested in differences between these EM means, which we're going to get to very shortly. Okay, what I do want to show you though is that I've saved the results of EM means into this object EMMME for the main effects model. When I just specify it on its own, it displays the EM means. And importantly, when I look at the class of this EMMME object, it's EMM grid. So when I use the contrast function in a moment, it requires this EMM grid object as an argument. Okay, I can add more variables to specs. So if I don't want it to average over female, and instead to give me separate estimates by male and female, I can put sex into specs also. So now it's giving me every estimated mean for each diet crossed with each sex. All right, so now I get 6 estimated margin means. Okay, you may be wondering, why are we going through all this trouble? Well, it's to get to the next step, which is the contrast step. So here's a note if you're interested about how the averaging works. I'm actually not going to discuss this today because in the end, all the other covariates are basically removed when we are getting to the effects estimate. So if you're interested in this, please go ahead and read over it, but I'm not going to actually talk about this. Okay, so now we want to do contrast among those EM means, which will be actually estimates of these effects. Okay. So as I mentioned, we didn't get an estimate of the effect of the high fat versus the high starch group. We only got comparisons versus the control group. Well, we can get that third comparison with contrast, right? And so the contrast is another function of EM means. And as I said, the first argument is that EMM grid object that's produced by EM means, all right? So that EMMME is going to be that first argument for contrast. Then for today's effects, we're always going to specify method equals pairwise. And method equals pairwise tells contrast to compare all the levels with each other, right? So it's going to compare control to fat, control to starch, and fat to starch, all level comparisons, all pairwise comparisons. You need to specify this because the default behavior is method equals EFF, which stands for effect coding, which instead is contrast with the average of all levels. And generally, we don't do that in regression. We don't as often compare to the average. That's more of an ANOVA style. So usually most people, when they're doing a regression, use pairwise instead. So we're going to be using method equals pairwise in all instances today. Okay. And finally, you specify the variable whose effects you want to estimate in simple. Okay, so this stands for simple effects, which will make sense pretty soon. But then you just put the variable that you want the effects of inside simple. So here I'm saying do all pairwise comparisons among the diets. And so these two we already got. One thing you may notice though, it kind of reverses the direction. The regression coefficients are interpreted as fat minus control and starch minus control. So you might notice that these are in the opposite direction of the original model. So these are positive here, 4.01, positive 3.45. Now they're negative. Okay, but only because it reversed the direction of the comparison. this is that last comparison we didn't get for free. So if you were interested in this comparison, now you can get it through contrast. You might have noticed this note here. So there is a note at the bottom of the output that tells you that there's been an adjustment made to the p-values. And emmeans will, by default, usually apply some kind of adjustment, and it varies based on what you specify here, for example, the method that you're using. Multiple comparison adjustments are way beyond the scope of this workshop. I'm just going to tell you there's another option that you can specify in a lot of these functions called adjust, which allows you to specify which kind of multiple comparison adjustment you want to make. For example, if you want no adjustment, you can say adjust equals none. There's actually quite a few adjustments that can be made. If you look at summary, the help file for summary.emgrid, sorry, I may need to fix something there. I'll have to look, it might need emmeans. Hold on, let me try this. Oh, sorry, I needed the package name in front of it. But basically, you scroll down in this help file here. There's a section called p-value adjustments, and you can see all the different adjustments that are possible here. Actually, more also in this list right here. So there's quite a few adjustments possible. As I said, though, it's beyond the scope of this workshop to discuss what those mean. So just know that it's a possibility you can control. Okay, then we just discussed estimating the effects of a categorical variable. And remember, the order of that procedure is first start with emmeans, then use contrast. If we instead want to estimate the slopes or the effects of a continuous variable, we're going to skip the emmean step and go straight to emtrends. Okay. In emtrends, the first argument is actually the model object that was created, for instance, by the LM function. All right, so we're not going to create an grid object. We're going to use emmeans. We're going to use just the model object instead. Then inside of specs, you're going to put the name of the variable across whose levels you want the slopes to be estimated. So for example, down here, I'm saying I want the slopes of some variable estimated across diet. The variable whose slopes you actually want is specified in var. So here I'm saying age, which is a continuous variable. So specifically with this emtrends, I'm putting the model object first, and I'm saying, give me the slopes of age across levels of diet. Now, when we look at the output, what do you notice? Well, you notice that all the age trends are exactly the same. That's not surprising because we have a main effects model, right? And in a main effects model, the variables effects don't depend on the other variables in the model. So this is totally expected. And this is exactly the same as the age coefficient itself that's in the summary of the LM object. Okay? Okay, then we're going to look at graphing. So graphing, we're going to use the EMMIP function. And the IP stands for interaction plots, but they can be used to plot predictions from any model, even if it doesn't have interactions. So we're going to start by plotting our main effects model effects. Okay, so basically what we're going to be doing actually is plotting predictions from the model, because plots of predictions are one of the most common ways to visualize the effects of predictors in the model. We're only going to be talking about a few of the EMMIP arguments today. There are a lot more to control the look of the graph. So we're not going to do much adjustment of the look of the graph today. That would take too much time. We're just going to talk about how to create these graphs. Okay. So the first argument to the EMMIP function is going to be either the EMM grid object that you created from emmeans, and we'll use this if we're going to visualize the effect of a categorical variable. If we instead want to plot the slopes of a continuous variable, we're going to specify the regression model object as the first argument. Then the second argument is a formula, all right? And the formula has at least two variables usually. There's going to be a break variable on the left side of the tilde, and then the x variable on the right side of the variable, on the right side of the tilde, excuse me. And what happens with this is that the variable that's on the right side of the tilde, the x variable, is going to be mapped to the x-axis. So whatever variable you want to appear on the x-axis, put after the tilde. The break variable is going to give you separate lines and colors. All right, and you'll see soon what I mean by that. If you want confidence intervals, there's a capital C, capital I, lowercase s for confidence intervals equals, and then it's either true, false. It is false by default, so you do need to turn it on true if you want them. Okay. Okay, and then if you want to adjust the labels, for example, of the x-axis, the y-axis, or the break variable, in the help they call it trace variable, but I thought break variable was slightly more, maybe more intuitive to you to understand what it means. That's what TLAB is for if you want to label the break variable. Okay, so we're going to use EMMIP first to visualize our diet effects. Okay, so remember that EMM object, EMM grid object we created way back here, right here, with emmeans, where we specify diet and sex. So essentially we get 6 estimated marginal means at each crossing of diet and sex, basically averaging over age at age 9. If I then supply it to EMMIP here, that object created by emmeans, then I supply a formula. So remember, the x variable goes on the right-hand side. So diet is going to be put on the x-axis, diet. And then the break variable is sex. So I get separate lines and colors by the break variable. And then I added the confidence intervals here, true. Otherwise, I would just get the dots and the lines. Okay, pretty easy, right? It turns out that this graph is actually a plot of those 6 estimated marginal means. And again, plotting predictions is a way to visualize the effects in your model, right? So for example, here, we can see that there are pretty noticeable diet effects that on average, the mice on the high fat and the high starch diet weigh more than the mice on the control diet. Similarly, we can see on average, male mice weigh more than female mice. But you'll notice that all the lines here are parallel, right? And this is the hallmark of the main effects model. If the lines are parallel, that means that the effects, for example, the effect of diet is exactly the same for the two sexes. And you'll notice that the gap between the sexes is always the same also, right? The distance between the 2 points for each diet is also the same, which tells us that the effect of sex is also the same across all the diets, okay? So whenever you see parallel lines, it usually suggests some kind of main effects model. If we instead want to graph slopes, we do not use an emmeans EMM grid object as the first argument. Instead, we're just going to specify the model object as the first argument. Okay, so here we're going to graph the slopes of age. And to do that, we're going to specify the model object, MME, which is created by LM as the first argument. Then the age variable is what we want to graph. So it goes on the right-hand side. It's the variable we want to appear on the x-axis. So it goes on the right-hand side. We want separate lines by diet, right? So we get separate lines and colors by diet. So it goes on the left-hand side. Now, when you have a continuous variable that you're graphing, you have to tell EMMIP at what values of the continuous variable do you want predictions. So here, we use the @ argument to do that. And always use a list like this. So basically, you put variables and their values inside of lists. So this list has a set of parentheses. Then inside those parentheses, we name the variable whose values we want to specify, and then we set it equal to a vector of values that we want to get predictions at. So we're going to specifically get predictions for each diet at ages 2, 9, and 16, right? So at 2, 9, and 16, I have predictions and confidence intervals. Okay. Again, X variable on the right-hand side, break variable on the left-hand side. I ask for confidence intervals too. Now, if you want, a more continuous looking confidence interval, you can specify more values of the X variable at which to predict, right? So here I only had it at 2 and 16, which are the min and max, and 9, which is the mean. But now let's say this specifies instead all numbers between 2 and 16. So this is 2, 3, 4, 5, 6, 7, 8, all integers. Now I have this graph, which has more confidence intervals, okay? Or I can specify even more. I can do every number between 2 and 16 in increments of 0.2. Here I have specified sequence, and this is, it returns a vector from the first number to the second number in increments of the third number. So from 2 to 16 in increments of 0.2. And you can see that I have a more continuous looking graph here. Okay. One really nice things about these EMMIP graphs is that you can customize them with ggplot code, right? So if you're familiar with ggplot, then here, for example, we are making the overall theme, which is kind of the overall look of the graph different. I'm changing the colors used with the scale color manual, and I actually changed the labels myself using labs. So all of this right here is ggplot2 code. Again, we don't have time or the scope today to discuss ggplot2 code, but for those of you that know it, just know that you can directly add it to this EMMIP, and it'll work just like you're specifying a regular ggplot graph. Okay. Additionally, if you want to start from scratch, there is an argument called plotIt in the EMMIP, and if you set it to false, it will produce a data set of what's being graphed. All right, so for example, here I say plotted equals false. I save that to an object that I'm calling plot data. If I look at the plot data, then you'll see it's actually plotting this y bar as the outcome. This is the confidence interval. And then this is the diet and age values that it's plotting it at. Then you can use this plot data and start from scratch, and you can create your own ggplot yourself from these data. And that's what I did here. So I used that plot data, and I'm not going to go over the code too much, but this is the graph created from this ggplot. So I used confidence bands instead here using geom ribbon, for example. Okay, so if you want to just make the graph yourself and not go through EMMIP, you can use this plotIt to save a data set of the values being graphed. Okay, so let's go to exercise 2. I'm going to do this one with you as well. And we're going to go back to the auctions data set to kind of practice. Okay. So in exercise 2, we're going to use the main effects model again, where bid is regressed on hours and rarity. And what I want you to do first is estimate the slopes of hours for each rarity, right? So in this previous model, we have hours and rarity. And I want this hours as a continuous variable, rarity as a categorical. So I want the slopes of hours across the 3 rarity levels. So if we're going for slopes, we want EM trends, right? EM trends. And if we're using EM trends, we don't need to do EM means first. So we're just going to go straight to EM trends. Remember, the first argument to EM trends is the model object, the regression model object. So that's the first one. So M1. Then I put the variable across whose levels I want to estimate the slopes inside of specs. So specs equals, and then I put a C, and then inside there, I'll put rarity. And the variable whose slopes we want, we put in var. So I put var equals age. I'm sorry, hours. I think my data set's screwed up. So hours, we want the slopes of hours across the rarities. Okay. When I run, or not library EM means. Sorry if I forgot to library EM means. You'll need the library EM means. My apologies. That's at the very top. Go ahead and run these 2 libraries if you haven't already. Going back here. Now that I've loaded EM means, here we go. EM trends. So you can see that these are the slopes of hours across the three rarities. Because we have a main effects model, it is all the same. Okay. Then we're going to plot the slopes using EMMIP, right? So it's EMMIP. The first argument is M1, the regression model object. Then comes the formula, right? Left side of the formula is the break variable. Right side is the X variable. So we want to break on rarity, and we want to put hours on the x-axis. So we go rarity tilde hours. Then we have to specify at what hours we want to evaluate this. And for now, let's just keep it simple at both 2 and 9 hours at the extreme. So hours ranges from 2 to 9 in the data set. So we're just going to use those two values. So I say at equals, and then list, and then go ahead and do open and close parentheses. Then inside of the list parentheses, you put age equals, and then C, and then inside the parentheses for C, you do 2, 9. Okay. So model object, break variable, tilde, X variable, at equals list, parentheses, inside the parentheses, the variable name equals, then a vector of the values at which you want to calculate the predicted oh, oops. What happened here? Oh, I'm sorry. I keep screwing up age and hours. My bad. Okay, let's try this again. There we go. Okay. If I wanted confidence intervals, I could also say CIs equals true. I'm sorry. I keep messing up hours and age like this. And for example, if you want more estimates, you know, you can add more hours. Like if I wanted 5, for example, here as well, I could just put 5 in there. And it'll give me an estimate of 5. So whatever values you want confidence intervals for and actual predictions for, specify them inside this app. Okay. Any questions on using the emmeans package so far? Everything that we're going to do with interactions is just a very straightforward extension of this. Okay. Then let's get to interaction models. So why are we going to model interactions? Well, an interaction allows the effect of a variable to depend on another variable in the model. Previously, we've been modeling main effects. And in those main effects models, we assume that the effect of a variable is the same across values of another variable. But interactions allow us to relax this assumption, right? It may not be actually true that the effects of age are the same across all diets. That's probably not true, actually. So we shouldn't probably run a main effects model if that is not true. Instead, we can run an interaction. So if we enter the interaction of a variable X and a variable Z into a regression model, we can answer the following questions. What are the effects of X at different values of Z? And these effects of X at specific values of Z are often called simple effects or conditional effects. So remember that word simple that we saw in contrast? That's where it comes in here. So in a main effects model, the effect of X is the same across all values of Z. On the other hand, in an interaction model, the effects of X will be different across values of Z. And those different specific effects of X are called simple effects, not main effects. Okay, so that's one of the questions. What are the different effects what are the different effects of X at different values of Z? And then another question that can be answered by this model is how different are the effects of X at different values of Z? Some people ask this, are the effects of X different at different values of Z, for example? So how, like if X is a continuous variable, like with the slope, how different are the slopes between them, for example? Okay. Now, what's interesting about interactions is that they're symmetric in the sense that if Z modifies the effect of X, X also modifies the effects of Z. All right, so we can also ask the questions, what are the effects of Z at different values of X, right? And so we can estimate the simple effects of Z at different values of X, or we can estimate the simple effects of X at the different values of Z. So from here on out, I'm going to really be making a distinction between the variables whose simple effects we want, and then the other variable, which I'm going to call the moderator a lot. All right. So if I'm estimating the simple effects of X, I'm estimating at levels of the moderator value Z. Okay. And that's why these are often called moderation models or effect modification models, because one of the variables is modifying the effects of the other variables. Okay. Okay, so how do we model interactions? We model them with product terms in regression models. So if I have variables X and Z, then I can create a product term variable literally by multiplying them together. I could create a variable that I call XZ that is literally X times Z. Now you can add these, you can create these variables yourself by multiplying them together, and you can stick them into your data set, but you don't have to do that because R provides a nice syntax shortcut that will basically create these interaction variables on the fly when you run your regression model. So there's no need to create these product variables yourself. You can just use this syntax in R. And that syntax is either a colon or a star. A colon adds just the product term to the model, whereas a star adds both the product term and the lower order terms. So these two specifications are the same, where I have the lower order terms diet and sex, and then diet colon sex. So that's both lower order terms and the interaction. Or I can specify diet star sex, which is exactly the same as diet plus sex plus diet colon sex. Okay, so those two are equivalent. Throughout the rest of this workshop, I'm just going to be using the star notation. So just know that that includes the lower order terms as well as the interaction coefficient. Now, if either X or Z is a categorical variable, then you'll have several dummy variables. And each one of those variables, like if X is categorical, each of the dummy variables representing X will be multiplied by Z. Okay, so you may have multiple interaction terms if you have categorical variables as well. We highly recommend that you enter these lower order terms in a model with the interaction, because if you don't, you're actually constraining some of the simple effects to 0, which often will result in a very badly fitting model. All right, so it's almost always the right decision to include the lower order term. I'm not going to be at all talking about significance of the interaction today. I'm just going to be modeling it and analyzing it whether or not it's significance. Okay, so that's not going to be a concern for us today. All right, so we need a general interpretation of these coefficients in interaction models. So for a model that includes X, Z, and their interaction XZ, predicting an outcome Y. So here we have X, the coefficient for X, Z, and its coefficient, and then XZ, which is a single product term variable, and its coefficient, which I'm calling X times Z right here, right? And we have the error term. The intercept is the same as always. And the intercept, again, is the expected Y value, the expected outcome, when X is 0 and when Z is 0. And when X and Z are 0, then you can guess that XZ is also 0, right? Because it's literally the product of X and Z. So when all the terms are 0, that is the expected outcome B0. BX though, this is where people screw up a lot. This coefficient is not a main effect anymore. All right, if you thought that, try to throw that thought out of your head now. What should be there is that this is a simple effect of X when Z equals 0. Okay, this is not a main effect. So this effect of X is now different depending on what Z is because of this interaction term. So this coefficient is strictly the effect of X when Z equals 0. Similarly, this Z coefficient is the effect of Z when X is 0. All right. So these lower order coefficients are simple effects when the other interactor is equal to 0. Then the interaction coefficient will represent a change in the simple effect or a difference between two simple effects. All right. So for example, this is the simple effect of X. Bx is the simple effect of X when Z equals 0. If I want to know what the simple effect of X is when Z equals 1, I actually take this bx and I add it to bx times z, these two together. And that will give me the simple effect of x when z equals 1. Another way of saying that is that the difference between the simple effect of x when z equals 1 versus when z equals 0 is this interaction coefficient. Okay, so think of interaction coefficients as changes or differences in simple effects. Okay, whereas the lower order terms are simple effects themselves. Okay. Yes, so in short, lower order terms are simple effects. Interaction terms are differences in simple effects. Okay, and remember the interaction works both ways. So not only is it the difference between two simple effects of x that are separated by 1 unit of z, it is also the difference between two simple effects of z when x changes by 1 unit. All right. I think this will become clear. If this is a little hazy or a little murky for you right now, I think it'll become clearer as we go along. But let me pause right now. Are there any questions about this? I know this is getting a little harder now. So let me pause for questions about the interpretation of these interaction coefficients. Filippo has asked a question in chat. When z equals 0, but 0 is not in the data or maybe doesn't make sense, that may make sense then to recenter 0 at a different value. Yes, and maybe you shouldn't really interpret that. That's going to come up later, actually, that exact point. I'll point that out when it comes up. Okay? Okay. If there are no other questions, I'm going to keep going, but of course, you can always ask questions in chat. All right, we're going to start then looking at a model with an interaction of two continuous variables. And the way I'm doing this is we're going to be looking at continuous variables first. We're going to be looking at categorical variables next, because the way you work with emmeans package differs depending on whether the effects variable is continuous and the moderator is continuous, and whether each of those is categorical. So first, we're going to discuss continuous variables. Okay, so now let's interpret the coefficients of a regression model that includes age, litter, the interaction of age and litter, and sex. Okay, so here I have the model, and I have age, litter, their interaction, and then sex. I've included sex because often in these interaction models, you're going to have other covariates that are not involved in the interaction. And I just want to kind of mention what emmeans is doing with them, although it's really not going to affect anything, to be honest. But I just want you to kind of know what happens. So here is the specification of the model. Sorry, let me not go too fast. We're using LM again, dependent variable tilde. Now we're saying age times litter, star, and the star again means both the lower order terms and the interaction, plus sex, right? Sex is not involved in the interaction, so I'm just going to add it like this. Then when I look at a summary of the model, I'll get the lower order terms for age and litter, and I'll have the interaction term here, and a single coefficient for sex. I'm going to go through the interpretation kind of quickly in the interest of time, but if you have questions, please just ask me, right? So again, the intercept is the expected outcome when all variables are 0, when all predictors are 0. So this is the expected outcome for a mouse who at 0 weeks, who comes from a litter of 0 pups and is male. All right. Now, this kind of goes to what Filippo was asking, which is, what if the variable 0, what if a variable has a 0 value on a variable doesn't really make sense? And litter is kind of like one of those variables. A mouse can't come from a litter of pups with 0 pups, because then there will be no pups in the litter at all. So the mouse wouldn't exist. So it doesn't really make sense to leave litter like this, but I'm not going to worry about that too much today. But yes, you're right that if I were to then interpret this, right, this is also going to affect this coefficient. So this coefficient for age, remember, is the simple effect or the simple slope of age when litter equals 0. And whether or not that makes sense, probably not, right? So maybe we shouldn't directly interpret this, but that's what the value is. All right, this is the value of the slope of age when litter equals 0. Similarly, this is the effect of litter when age equals 0. And so this is another lower order term, which we interpret as a simple effect when the interacting variable is 0. All right, so then we have the interaction coefficient. This represents the change in the age slope for each additional pup, or the change in the litter slope for each additional week of age. So the slope, for example, of age for a mouse from a litter of 1 pup is this coefficient plus this times 1, for example. And I'll go over more of these calculations in a second. Then we have the sex coefficient, which is that females are expected to weigh minus 1.6 grams less than males, no matter the age, no matter the litter, right? It doesn't matter what those values are because sex is not involved in that interaction. All right. Okay, so let's look at these a little bit closer. Remember that these lower order terms are the effects of age when litter is 0 and the effect of litter when age is equal to 0. And then the interaction is then some change in that effect when we change the interacting variable, the moderator, by some amount. We can estimate the slope of age at any litter size using this simple equation. Okay, the age effect at a particular litter is going to be the age coefficient plus the interaction coefficient times the litter size. All right, so for example, if litter is 0, it's going to be b age plus the interaction times litter equals 0 times 0. So that goes away, right? And what we're left with is just the age coefficient. So now you can hopefully see that that's why this age coefficient is literally the simple effect or the simple slope of age when litter equals 0. But what about the slope of age when litter equals 2, which is the smallest value in our data? Well, we take the age coefficient, add it to the interaction times 2 in this case, right? So it's 0.67 minus the interaction times 2, which turns out to 0.63. And we can do it for any litter value, times 10 here, right? So age coefficient plus the interaction times 10 for the age effect at litter equals 10. What you'll notice then is that as litter size is getting bigger and bigger, the age slope is getting less and less positive, right? So what we can conclude from that, basically, if these data are real, is that mice that come from larger litters tend to grow slower over time, right? That's kind of what we're getting from this. Now remember that interactions are symmetric. Not only can I calculate age effects at different litter sizes, I can also calculate different litter effects at different ages. And it works exactly the same. I just take the litter coefficient and then add to it the interaction coefficient multiplied times age. So for example, the litter effect when age equals 8 is the litter coefficient 0.024 plus the interaction coefficient, which is also 0.024. I'm sorry, it's negative 0.024 times 8. So this is the litter effect at age 8. And so what this suggests is that the litter effect is getting more and more negative as mice get older. Okay. 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 So we now are maybe interested in estimating the simple effects of one or two of those variables, either one of those variables, across levels of the other moderating variable. Okay, so we're going to use as an example, we're going to estimate the simple slopes of age at different values of litter. For this problem, I'm going to be thinking of litter as the moderator, and because we want to look at the effects of age. So when I say the moderator here, I'm referring to litter. When the moderator is continuous, like litter is, we have to choose values at which to estimate the slopes of the effects variable. So I have to choose values of litter that I'm interested in for the slopes of age. And when you're choosing these values, there are many common choices. The best choice usually is substantively meaningful values. So for example, if your moderator is age, you might want to choose like 18 or 21 for US citizens. Or if your moderator is blood pressure, you might want to use cutoffs for high blood pressure or extreme high blood pressure, for example. But you don't always have those substantively or clinically meaningful values. In other cases, you might have to use like the minimum and the maximum, or some sample quantiles, like the mean and the mean plus a standard deviation and the mean minus standard deviation. This is very common too, mean and the mean plus and minus the standard deviation. When you don't know what are important values of this variable, this is a very common fallback, because it gives you a kind of nice spread of values across the moderator. Okay, I'm going to choose the minimum, the maximum, and the mean here, just for my own, no real reason other than to demonstrate. Okay, so the min and max of litter are 2 and 10, and the mean is 6. So those are the 3 values of litter I'm going to evaluate the age slopes at. Okay, so I want the age slope at litter 2, the age slope at litter 6, age slope at litter 10. All right. So we're going to use EM trends, right, to do this, because EM trends is what we use to estimate slopes. All right. The first argument in EM trends is the model object. Then specs, remember specs in EM trends is the name of the variable across whose value you want to estimate the slope. So here's really going to be the moderator variable. So here we're going to specify litter. And then var is the name of the variable whose slopes we want. So this is going to be age. And then remember, we need to specify values of the moderator. And here we're going to do it in at. So we say at equals, then we're going to use a list. Inside the list, we put the moderator and a vector of values at which to evaluate these slopes. Okay, so here I'm saying the model object specs equals litter, the moderator, var equals age, and then the list of the moderator values. And then when I output that, I get 3 age trends. Now they're different, right? This is the age slope at litter size 2, age slope at litter size 6, and age slope at litter size 10. And you can see now they're different because this is an interaction model, right? You automatically get the confidence intervals for these slopes. And you can see, for example, that the slope is decreasing, as we said before, the slope of age is decreasing with litter size. So again, mice that come from larger litters tend to grow slower over time. If you need p-values for these slopes, you just put the object created by EM trends inside of test. And instead of the confidence interval, you'll get these p-values instead. Okay. Any questions on so far on estimating these simple slopes? I hope it's pretty straightforward. Okay, then let's try to visualize the interaction of 2 continuous variables. So we're gonna now visualize what we just estimated, the slopes of age at different litter values, right? To graph the slopes, we use the regression model object again as the first argument. We're gonna be using, EMMIP to graph. And once again, for slopes, the first argument is the model object. Then we do the formula, right? And on the left side is the break variable, which is the moderator. And on the right side is the variable that we're going to map to x, which is the slope variable here, age. Okay, so litter tilde age. For graphing, we need to specify both values of the x variable if it's continuous, and for values of the moderator if it's continuous. So when you're graphing, if there's a continuous variable, you're going to have to specify values for it, basically, period. All right. So in this case, since they're both continuous, both the moderator and the effects variable are continuous, I have to specify values of both. So here is the resulting graph. So I do all of that inside of list. I specify both values of age and values of litter inside there. So I want estimates across each integer of age between 2 and 16. And then specifically, I want those age slopes at 2, 6, and 10 litter size. All right. And then this is the resulting plot. And you can see that the age slopes are steeper as litter size gets smaller, right? Or they get less steep as litter size grows larger. And we get estimates at each age from 2 to 16, which is where you see the confidence intervals. Okay, very, very easy to do, right? In EM means and EM trends and EM MIP. Okay. Let's do this as an exercise. Now, this time I'm going to let you do this and then we'll go over it at the end. So if you've been following, I want you to use the auction data set. I want you to first run a linear regression model where bid is predicted by hours, quality, and their interaction. Then I want you to estimate the simple slopes of hours at each quality from 0 to 5, and then graph the simple slopes of hours at each quality from 0 to 5. Okay, so we're going to concentrate on hours being the effects variable and quality now as the moderator. And again, the exercises are rewritten for you at the bottom here, so you should be able to just continue down here if you like. I'm going to give you 3 minutes to work on this. I know that may not be enough time, but at least it'll get you started. And yeah, I put a timer up here. Just go ahead and start. And then after 3 minutes, we'll go over them together. And then after that, we'll take a break. Okay, let's try working through these together. I'm going to type a little quicker now since you've had time to work on it. Okay, so the first is run a model with the interaction of hours, quality, and their interaction. So I'm going to use LM. It's going to be bid, tilde, hours, star, quality, right? That includes the interaction and the lower order terms. And then I'm going to put data equals auction. Okay. I'm going to save that here. I'm just naming it after the exercise number. So this is going to be M3. Okay, so hopefully that was straightforward. Then we want the simple slopes of hours at each quality from 0 to 5, right? So for estimating simple slopes, we're going to go to EM trends. And the first argument is the model object, which is M3. Inside specs, we put the moderator, right? So I'm going to put specs equals C and then liter. So keep doing this quality. And then the slopes we want are for hours. So after vars, I'm going to put hours. And then I need to specify the values of the moderator inside of at. So I put at equals, then list, parentheses. Inside the parentheses, I say quality. And you could have done C like 0, 0, 1, 2, 3, 4, 5. Or you can also just do, as I've done before, 0, colon. Okay. And then you should have gotten this, which is the 6 age slopes across the qualities. And as an exercise, what coefficient is this age slope minus this age slope, for example? Minus 0.8, oops, sorry. Minus 0.8322, minus 1.7557, 0.9235. And if I look at my summary of my model, okay. Finally, we want to graph them. EMMIP, model object is the first argument. The formula, break variable on the left, so we put quality on the left. Hours is on the right, because we want to put hours on we want the slopes of hours, so we specify it as the X variable. Then after at, we're going to put the list of values for both of them, right? Because when we're graphing them, we need to specify ranges of the effects variables. So hours goes from 2 to 9. Maybe I should have said that. It doesn't really matter. You can specify whatever values and it'll work. Hours equals 2 to 9. And then for quality, I'm going to say from 0 to 5. And let's say CI is equals true. And you can also always abbreviate true with just capital T if you like. And there I go. Okay, so these 5 slopes are represent these 5 estimates themselves. Right? So the 0, the negative one is the red one, right? And the most positive, the blue, is the one at liter equals 5, which is this. Okay, any questions on this? Okay, then let's take a break. That is the 5-minute mark, so let us continue. Here and here. Okay, so we've now looked at how to analyze an interaction that involves continuous variables, let's see how to use emmeans to analyze interactions with categorical variables. So now both the effects variable and the moderator are going to be categorical. So we're now going to model an interaction of diet and sex, and we'll also add age as a covariate, again with weight as the outcome. Now remember, diet is represented by two dummy variables, one for fat and one for starch, and sex is represented by one dummy variable, which represents one for females, 0 for males. When we create the interaction, we take the two dummy variables for fat and starch and multiply them by the dummy variable that represents female. And so we'll have two interaction coefficients as well, right? So we have lower order terms for fat and starch and lower order term for female, and then two interaction coefficients, which is basically these two variables, the diet times fat times female and starch times female right here. Okay, and we also have a main effect of age. So a specification again is diet star sex, right, for the interaction in lower terms plus age. Here is the model. I think we all know how to interpret the intercept by now. It is the expected outcome for the control mouse who's male at week 0. Now these diet effects are not main effects, right? These are specific effects when female equals 0, all right? And when female equals 0, that means male. So this is the comparison between fat and control specifically for males. And this is the comparison of starch versus control, also specifically for males. Okay, so do not mistake these for main effects. This female coefficient represents the difference between females and males when diets are equal to 0, right? So when females interacted with both fat and starch, and when both of those are 0, what does that mean? That means control, right? So this is also a simple effect of female versus male when they're on the control diet. Okay, so again, do not mistake these lower order terms as main effects. They are simple effects when the interacting variable is equal to 0. And in this case, when the interacting variable is a categorical variable, we can just call it the reference group. So these are the diet effects for the reference sex group, male. And this is the sex effect for the reference diet group, which is control. Age is a main effect, so it does not depend at all on these other effects. Okay, then these two interaction coefficients represent changes in effects again, or differences in simple effects. So for example, this is the fat versus control for males, right? This, in other words, males on the fat diet are expected to weigh 4 grams more than males on the control diet. This is a change in that diet effect for females, if you compare that to males. So females on the fat diet are also, this is a very, very small change, right? So essentially you can think of the fat versus control comparison being essentially the same between the sexes because this number is so small. On the other hand, this number is not that small. And this says that this is the starch versus, this coefficient is starch versus control for males. If I want to know what starch versus control is for females, I add this number to this number, these two coefficients together, right? So 4.09 plus minus 0.12 is the starch versus control comparison for females. So again, this is the difference in diet effects across the sexes. Or, remember, interactions are symmetric. It's also the change in the sex effect across diets. So this is the sex effect for the control diet. If I want to know the sex effect for the starch diet, I add these two coefficients together. Okay? So always remember, keep remembering this. Lower order terms are simple effects when the interacting variable is 0. Interactions are changes or differences in those simple effects. Okay? Okay, so we might want to look at those simple effects across levels of the moderator. And we're going to use the same procedure we did before for looking at effects of categorical variables, where we start with emmeans and then go to contrast. Okay, so remember the first argument is the model. Then we're going to now put all the variables involved in the interaction inside of specs. Then we get estimated marginal means. It's going to average across age here, because that's another covariate that I did not specify in specs. But now we get separate estimates by diet and sex here for each combination of diet and sex. Okay, that's the first step. So I save that into this EMM diet sex object, which is an EMM grid object, which we have to use for contrast. Then we're going to specify exactly as we did before, method equals pairwise for all pairwise comparison among the levels, and then simple equals diet. So simple, the variable in simple is the effects that we want. So we want diet effects here. So it's going to give us separate diet effects for the two sexes because I put sex in specs. Excuse me. So this is that specification. Now you can see we have 3 sets of diet effects for males and 3 sets of diet effects for female. And as we said before, control versus fat is not very different between the two, but control versus starch is somewhat different looking between the two, as is fat versus starch. Okay, so you can get an idea then of the simple effects of diet for each sex using this emmeans contrast. If you need confidence intervals, by the way, on these contrasts, so notice here for contrast, it automatically gives you p-values. If you need confidence intervals for these contrasts, you can put them inside of constant. Okay. Now remember that the interaction is symmetric. So not only does sex moderate the diet effects, diet moderates the sex effects, right? So we can also look at the simple effects of sex across diet. And all we do is just change what's inside of simple. So now we're saying we want the effects of sex, right? When we specify simple equals sex. So now we get 3 sex effects, 1 for each diet. And we can see that the sex effect looks pretty consistent between control and fat, but there's a larger difference between the sexes on the starch diet, for example. Okay, so this is how, usually, one of the easiest way to decompose an interaction or to analyze it is to look at the simple effects and to try to understand the simple effects and then how they're different from each other. Okay, you can also do interaction contrasts. So if you want to take differences among these effects. So for example, if I want to look at the difference between the control fat comparison between the two sexes, or if I want to look at the sex effect in the contrast group versus the sex effect in the control group versus the sex effect in the fat group, this is where interaction contrasts come in. So there's another argument inside of contrast that's called interaction. And if you set it to true, it will then compare the simple effects. It'll take differences among them. So for instance, this is a comparison of the fat versus control between males and females. So how different is the fat effect between males and females? Not very different. It's also the sex comparison compared between the sex contrast or the sex effect contrasted between the control and fat groups. So how different is the sex effect between the control and fat groups? Not very. These, by the way, are actually just our interaction coefficients directly. So this 0.0443 and 1.28 are actually directly estimated in our model, those two. But the third one is not something we get for free. So if you wanted to know, for example, whether the sex effect is different between a fat and starch group, this is where you would get that estimate. Okay. In diet pairwise, the estimate is always related to male compared to female. If you're talking about here, this is contrasting 2 diets within each sex. That's what's going on here. So we're looking at the simple effect of diet for males and the simple effects of diet for females. So simple represents the effects you want. The other variable then is going to be the moderator. So here I would consider sex the moderator, and we're looking at the simple effects of diet in the case. Okay, so we then might be interested in graphing the interaction, and it's going to go exactly as we did before, where we're going to specify the EMM grid object as the first argument. Okay, so for example, we created this EMM diet sex here with emmeans, right? That is an EMM grid object, which is the first argument to EMM IP. Then again, we have the break variable, separate lines and graphs, separate lines and colors by sex, and then diet will be on the x-axis, okay? And I ask for confidence intervals again. Now the lines aren't parallel anymore, right? So now we know we're not in a main effects model. And when the lines look very non-parallel like they do here, that is an indication of an interaction. So while the control versus fat comparison looked quite similar between the sexes, the starch versus control or starch versus fat does not look the same. So really, the interaction involves mostly this starch. They react to starch differently, for example, the sexes. And we can see that in this graph. Okay. You may instead, though, be interested in the sex effects at different diet levels. And if generally, I would say put the variable whose effects you want on the x-axis and then make the moderator the break variable. So if you're interested in sex effects, put sex on the x-axis and put diet as the break variable, as the moderator. Now it's easier to see the sex effects, right? We can see that the sex effects are pretty similar between the control and the starch groups, right? They look pretty parallel. But then the green and the red. The green and the red are the fat and the control groups. Those look pretty parallel, but the blue one looks more steeply negative. So that is the interaction, is that the sex effect is different in the starch group from the other two groups, basically. Okay, so it depends on what effects you want to visualize, where you're going to put the variables, either on the x-axis or as the break variable. Okay, so it's time for another exercise. Let's do this with our categorical variables. So now I want you to use the auction data set, and I want you to run a linear regression model where bid is predicted by rarity, budget, and their interaction. So hopefully earlier you made factors out of rarity and budget. This will work even if you didn't, but the order might be a little off, but it'll work. And then estimate the simple effects of rarity across budgets, and then graph the simple effects of rarity across budgets. And again, I'll give you 3 minutes to do this, and then we'll come back and, and we'll discuss it. Okay, there's a 3-minute timer. And if, of course, you have questions you want to ask while we're doing this, feel free. Okay, about 1.5 minutes left. Okay, about 30 seconds left. All right, that is about time. Let's do these, go over these together. Give me 1 second. No, share screen. Okay. All right, so now we're on exercise 4. I wanted you to run a linear regression model predicted by rarity and budget. I'm sorry, and their interaction, I should have said. Okay, M4, LM, bid, rarity, budget times budget, right, for the interaction and lower order terms, data equals auction. You want a summary. I forgot to put summary earlier, but summary is how you look at the regression. Right. Okay, now we want the simple effects of rarity across budgets, right? So when we want simple effects of categorical variables, we start with the emmeans step. So we're going to do EMM. M4 is what I'll call the object. emmeans, right? First argument is the model object, M4. Specs, we put both variables involved in the interaction inside. So I'll just put rarity. Oops, I forgot my C. Rarity, and then budget inside of C. And then that's it, sorry. Okay, then to get the simple effects, I'm going to use contrast. First argument is the emmeans object. Then I always put method equals pairwise for all pairwise comparison among the levels. And then I put the variables whose effects I want after simple, right? So I said the simple effects of rarity across budgets. So I put simple equals rarity. Okay, and then remember there are 3 rarities and 2 budgets. So these are the differences in the expected bids between each of the rarities for each of the 2 budgets, right? And you can see that the same comparison is quite different across. Okay. And then we want to graph the simple effects of rarity across budgets. So I'm going to do EMMIP for that. If we're doing simple effects of categorical variable, I can use the emmeans object, EMM_M4. Then I need a formula specifying what goes where. So I want the simple effects of rarity, so it'll go after the tilde. And the moderator here is budget, so it'll go before the tilde. Okay, and this is the interaction, right? So you can see the lack of parallelism among these lines, and that suggests an interaction here. So for example, the difference between rare and unique is quite a bit larger for a large budget than it is for a small. This line is much steeper, whereas this line is less steep. The difference between common and rare is smaller for a large budget than it is for a small budget, right? So that's the interaction that we're talking about. Any questions on this section so far? Okay, then the next section is actually kind of a straightforward extension of these 2 previous sections. So now let's pretend one of them is categorical and one is continuous. There's actually nothing really new in this section. So I'm going to go over pretty quickly, try to get to the exercises. But now we have 1 categorical variable, 1 continuous variable. We may be interested in the simple slopes of the continuous variable at different levels of the categorical variable. That's actually the more usual way. But sometimes you're also interested in the effects of the categorical variable at different values of the continuous variable. So again, either variable can be the moderator. It just depends on your research question. And we can do both kinds of analyses quite easily, but all we're going to do is run a model. So now I'm using diet as my categorical variable and age as my continuous variable. And since there are 2 diet dummies and 1 age variable, there's going to be 2 interactions as well. So here we have the lower order. So these are the effects of diet, age equals 0. This is the effect of age when the diets are 0 for the control diet, right? So once again, lower order coefficients are simple effects when the interacting variable is 0. And then these interactions represent changes in those effects. So for example, this is the slope of age for the control group. The slope of age for the diet, for the fat group is this plus this, right? This represents the difference in the age slopes between the fat diet and the control diet, for example. Or another way of interpreting it as this is the difference between fat and control for each additional, I'm sorry, let me start over. This is the fat versus control comparison when age equals 0. For each additional week, the fat versus control comparison increases by this much. All right, so over time, fat and control are getting farther and farther apart. All right. Okay, so again, we've basically done everything in this section before. If we want to estimate the slopes of age, I'm going to use EM trends, and I'm going to specify diet here. And now you can see I have my 3 age trends across the 3 diets. As expected, the age trends for the high fat and high starch groups are much more positive, which means that each week, these mice on these fat and starch diets grow faster than the mice on the control diet, right? Or we might be interested in the effects of diet at different ages, right? If I'm interested in treating diet as the effects variable and age as the moderator, I'm going to go back to EM means first, right? So EM means here, I'm going to specify both variables and specs, and then I'm going to supply a list of ages at which I'm going to evaluate the effects of diet, okay? But first I start with EM means, and then I get a list of EM means for each diet at these ages, right? So this is the estimated weight for like a control mouse at age 2. This is the estimated weight for a control mouse at age 16, okay? And then basically by taking contrast among these estimated marginal means, we'll get the simple effects. So after creating this EM means object, I can go straight and put that object inside of contrast. I put method equals pairwise, and then simple equals diet, and I'll get all of the diet effects across each of the specified ages, right? So I specified age 2, age 9, and age 16, right? So these are the diet comparisons at age 2. These are the diet comparisons at age 9, and these are the diet comparisons at age 16. And for example, you'll see that control and fat and controller starch are getting farther and farther apart as age goes on, right? As the mice get older and older. Now I can visualize these in the same way. If I want to visualize the slopes, then I start with the model object. Age will be the X variable. Diet will be the break variable. And I'll specify a list of ages, as I've done before. And so I'm just saying I want age predicted at 2 to 16. So I'll get confidence intervals at every integer from 2 to 16, right? Very straightforward. Instead, we want to plot the specific diet effects at different ages. We switch the formula, right? And I use the EM means object that I created before. So when we're graphing effects of categorical variables, we use the EM grid object first. Then age is now the moderator, and diet is going to be depicted on the x-axis. And so we can see that at age 16, the 3 groups are much farther apart than they are at age 2, where they're much closer together. Okay, so it depends on what you consider the moderator and what you consider the x variable. The variable whose effects you're interested in is going to determine which graph makes more sense to you. The interaction depicted is actually the same. You know, believe it or not, these 2 graphs are showing you the same thing pretty much, just depicted in a very different way. Okay, so I'm going to go ahead and run this exercise together with you since we went over that section very fast. But I just want to stress that the 2 previous sections gave you all the tools you need to do this. So let's do this together. All right. Okay, so using the auction data set, I want you to run a linear regression where bid is predicted by hours, rarity, and their interaction. Okay, so I'm going to call this M5. And we're going to run a linear regression where bid is predicted by hours times rarity. And then the data is going to be auction. I know I'm typing kind of fast. Let me slow. So model object, LM, bid, tilde, hours, star, rarity, data equals auction is the data set. Okay. If I get a summary of this, I should see two interaction coefficients, right? Because there are 3 rarities. So I'll see 2 dummies. This is the simple effect of hours for the common rarity, right? When rare and unique are 0, that means it's a common item. So this is the simple effect of hours. For common items, these are the effects of rarity, like rare versus common when hours equals 0, and unique versus common when hours equals 0. Again, hours equals 0 doesn't really exist on our data set. The lowest value is 2, so maybe we shouldn't directly interpret these too much. Then these will represent differences in either the hours slope between the rarity groups or the difference in rarity effects as we increase hours. Okay, so let's analyze this interaction. There's a couple ways we can do it. Let's look at the slopes of hours at different rarities. Okay, so to get slopes estimated, we go straight to EM trends, right? And then I specify first the model object, M5. Then for specs, I put the moderator variable, which is rarity. And then for var, I put the variable whose slopes we want, which is hours. Okay, so this should return 3 slopes, 1 for each rarity. Right, so we can see that the slope of the slope of hours is positive for rare and unique items, but it's actually negative for common items. Right, so this is the interaction, that the slopes are not the same across levels. Or I can estimate the effects of rarity at different hours. To do that, remember I start with emmeans, and then the model object is first. Then in specs, I put both variables. Yeah, I put both variables involved in the interaction, which is rarity and hours. Okay. And then I have to, since now hours is the continuous moderator, I have to specify a list of values at which to evaluate this interaction. Okay, so I'm going to put add equals and then list. Inside the list, I specify the moderator and the values that I want to evaluate it at. So for now, I'm just going to evaluate it at 2 and 9, which are the min and max. And so this is just the estimated marginal means. Sorry, let me save that as an object, EMM5. Okay, then I put this inside a contrast, right, to get the simple effects. So M5 is the first argument to contrast. Then I put method equals pairwise to contrast the actual levels of rarity. And then I say simple equals hours. Now I get the, I'm sorry, that should be rarity. I want the simple effects of rarity at separate hours. Sorry, so that should have been rarity. So now I get 2 sets of rarity comparisons, 1 for hours equals 2 and 1 for hours equals 9. And again, you can see that the rarity differences, especially the first 2 comparisons, are much larger at 9 hours than they are at 2 hours. That is the interaction, right? How the rarity effect changes with hours, or how the hours effect changes with rarity. Then I can plot these both, right? If I want to plot the slopes of hours, I go to EMMIP, and the first argument is the model object N5. Moderator goes on the left side of tilde, so I'll put rarity, tilde. Hours is what effects we want to view, so it's the X variable, okay? And then I need to specify again a list of hours. So I'm just going to use the same, just 2 for now, to keep things quick and simple. At equals list, and then inside parentheses, hours equals C. I'll just do, actually, I'll do 2 to 9 to even keep it simpler. All right, so this is just for graphing every estimate between 2 to 9. Oh, I forgot my confidence intervals. Okay, so model objects, break variable, X variable, and then at which values do I want confidence intervals, basically. Okay, then if I want to, these are the slopes, right? And again, here we can see these match these estimates right here. The common slope is negative, and the rare and unique slope are both positive and pretty similar, which is why they look nearly parallel. They're actually a little bit different. Now I might want to instead graph the simple effects of diet, simple effects of rarity at different hours. So to do that, I'll use EMMIP again, but instead now I'll put the EMM M5, the EMM grid object, as the first argument. Okay, then I'm going to switch the formula because now I want hours to be the moderator. Goes on the left side. I want rarity to be displayed on the x-axis because I want to look at the effects of rarity. And then that's all. That's all I need for this. And then I'll say CI is equal true. There we go. And here we get the rarity effects at 2 hours and 9 hours. And once again, you can see that the lines cross, which suggests an interaction. But to interpret this, we would say that in general, the differences among the rarities are much more pronounced, especially between rare and common at 9 hours, right? So this difference becomes much larger in hours. Okay, so that is our sections on linear models. Are there any questions before we move on to generalized linear models? Okay, I know you've been asking a lot of questions in chat, so keep doing that if that works for you, but you can also unmute if you'd like to ask. Okay, so there are a few more considerations when we're in generalized linear models rather than just regular or linear regression. The methods that we've been using so far will continue to work also for GLMs. And GLMs include models that you may be familiar with, like logistic and Poisson regression models. These GLM models use a link function, which transforms the outcome, which usually has some limited range, to a variable that can take on any value. And this transformation is what allows us to model linear relationships with the predictors. So for example, in logistic regression, the actual outcome is some probability between 0 and 1, but it's hard to model a linear relationship with like a continuous variable, let's say like age, when the value of the variable can only go from 0 to 1. So what we do is we apply this transformation, which is this logit link, which transforms the variable that ranges from 0 to 1 to a variable that ranges from negative infinity to infinity. Okay. So there's this link function that kind of allows the variable, the outcome variable, to be expressed in 2 different scales or metrics. The predictors will have a linear relationship with a transformed outcome. So like in logistic regression, we're transforming probabilities to what are called log odds or logits. So the predictors have a linear relationship with the log odds of the outcome, not with the probability of the outcome. And so that is one thing that will kind of complicate our estimation of these effects, because the relationship between probabilities and the predictors is actually nonlinear. So we'll show you a quick example here. So remember, we have that hypertension variable in the mouse data set, and it is a 0-1 variable that codes for whether the mouse has hypertension or not. And we're going to look at that as a function of age here. And so now, though, notice instead of LM, we're using GLM for generalized linear model, and we're specifying family equals binomial, which will basically run a logistic regression model, right? So this is appropriate for a 0-1. Now, as I mentioned, logistic regression uses this logit link, which transforms probabilities that range from 0 to 1 to log odds that range from -infinity to infinity. So the age variable has a linear relationship with the log odds, right? So this was a 0, 1 variable, but now you're seeing these negative values, which do not exist in the original 0, 1 variable or in the probabilities that range from 0 to 1. So we know that this is on the transformed metric. And here you can see clearly that age has a linear relationship with the log odds of hypertension, okay? Or the logit of hypertension. But it has a curved relationship with the probability of hypertension. So what I did here is I actually added type equals response to EMMIP, and that transforms the outcome to its original metric, which here is probabilities. All right, so now you can see probabilities on the y-axis, and you can see that age has a curved relationship. In logistic regression, continuous variables actually have an S-shaped relationship with the probability of the outcome. So right now I plotted from ages 2 to 16, but if I extend my plotting to ages 0 to 50, you can see the S shape here, right? So for any continuous variable, if I extend the range far enough, you'll eventually see an S shape in logistic regression. So the advantage of plotting the predictor against the transformed outcome, like the logits here, is that you'll see the straight lines and you can use parallelism as kind of as a guide to determine whether there seems to be an interaction or not. But the problem with plotting it on this scale, I'm sorry for scrolling so much. The problem with plotting it on this scale, the log odds scale, is that people don't have a good idea of what the probability is when log odds equals -3. So it's harder for people to interpret what is the change going from -3 to -2.5? Like, how much is that a change in probabilities? That's not really easily interpretable for a lot of people. So although you get a nice straight line here, you don't get an outcome that's easily interpretable in terms of probabilities. So it has advantages and disadvantages for plotting it either in the transformed log odds metric or in the probability, the original metric. If you plot it as probabilities, people can, yeah, definitely say, oh yeah, between 20 and 30, it raises, you know, let's say that's like 30 to 65, like 35.35 probability change between 20 and 30. That's much easier for people to interpret than log odds. But what'll be harder is judging the parallelism of these lines. And in fact, lines that are not parallel in one metric may look more parallel in the other one. And that can be a little bit confusing. So that's one decision you'll have to make, is how am I going to present these results in a graph? Another concern is that the effects can often also be presented on two scales. So in logistic regression, the coefficients that you get are interpreted as differences in log odds. And again, those differences are represented by those straight lines. And so they're easy to interpret in terms of differences, but again, the differences are measured in log odds. And so that's hard for people to know. Like if I said, you know, a 1 unit increase in age increases the log odds by 0.5, it's hard for people to know how much of a change in probability that is. So sometimes, you know, you may want to express them in terms of the raw coefficients, or you may want to express the transformed coefficients. So in logistic regression, one transformation of the coefficients that's often done is exponentiating. And when you exponentiate the coefficients in logistic regression, they're interpreted as odds ratios, all right? So you have choices now in how you want to express the simple effects. For example, in logistic regression, we can express them as log odds, or we can express them as exponentiated coefficients, which are odds ratios. And we can choose to graph the interaction on the original log odds scale, or we can graph it on the probability scale. And each of them has their advantages and disadvantages. Okay. So we're going to do an example of a logistic regression model. So here we're going to be modeling the probability of hypertension which is again a 0-1 variable in a logistic regression that includes diet and age and the interaction of diet and age. So we're going to have the same sets of coefficients that we did in linear regression, but they're going to have a different interpretation because now we're modeling them in a logistic. Right, so here I'm going to do GLM, again with family equals binomial to specify a logistic regression. Hypertension is being predicted by diet and age and their interaction and litter. Okay, and then when I get a summary of these coefficients, the summary will by default be expressed in the transform metric. So these are differences in log odds. All right, so this diet fat coefficient is again a simple effect. So this is the simple effect of fat versus control when age equals 0. So another way of saying this is that at age 0, the fat group is expected to have minus 0.4, I'm sorry, the fat group is expected to have 0.422 lower log odds of hypertension than the control group. Let me say that again. At age 0, the mice on the high fat diet are expected to have 0.422 lower log odds of hypertension than mice on the control diet. Again, it's hard for people to know how big of a change 0.422 is in log odds, but that's what you get by default out of logistic regression. Also, just as before, this age coefficient is the age slope for the control group, right? When fat is 0 and starch is 0. So we can say that for each additional week, the odds for the control group, the log odds of hypertension for the control group decreased by 0.03. Okay, so again, expressed in log odds, and then these interaction coefficients are interpreted as differences, again, in simple effects when we change diet groups or when we increase age by 1 unit. Okay, so the slope of age for the fat group, for example, is this coefficient for age plus this interaction coefficient, which again, though, is expressed in how much the log odds of hypertension change for a unit increase in age for the fat group. It's not easily interpretable. So we may instead want to use odds ratios, which a lot of people are more comfortable interpreting than changes in log odds. And the way you do that is you just exponentiate the coefficients. So here I took coef of the model object m hyper. So I'm sorry, m hyper is the name of the model object right here. And then if I put that inside of coef, it returns the coefficients. And then I put that inside of exp, which exponentiates them. So this is actually not interpreted as odds ratios. The only thing that are actually odds ratios are these lower order effects. So these are the only things that are actually odds ratios. This is the expected odds of hypertension for control mouse at age 0 from a litter of 0. All right. These are odds ratios. This is the odds ratio of fat versus control for a mouse that's 0 weeks old. All right. This is the odds ratio of starch versus control for a mouse that's at 0 weeks. This is the odds ratio for age. So how much the odds change per unit increase in age. So you can see that the odds are going down for each. The odds of hypertension for the control group are going down. All right. I don't want to go too much in the interpretation of logistic regression coefficients because it could take a long time. But also realize that these are not odds ratios, and the interpretation of exponentiated coefficients in logistic regression is kind of tricky. And the simplest way of putting them is that it's a ratio of odds ratios. So for example, this is the odds ratio for age for the control group. If I got the odds ratio for age for the fat group, and I took the ratio of those two odds ratios, it would be this number right here. So the slope, the odds ratio for age is 1.26 times bigger in the fat group than the odds ratio for age in the control group. And so you can think of this as some multiplicative change in an odds ratio or in the ratio of odds ratio. Either way works. But those coefficients, exponentiated interaction coefficients, are kind of tricky to interpret. So don't worry if it's a little confusing. We're going to use emmeans to, again, help us to interpret this interaction. Okay, so let's start with estimating the simple effects in this logistic regression. And the procedure to estimate the simple effects across levels of the moderator are going to be the same as before, right? So we're going to first start with the emmeans function to estimate the estimated marginal means. And we're going to estimate the diet effects at ages 2, 9, and 16. Okay, so here we're going to use emmeans again, putting the model object first, putting the interacting variables and specs, which are diet and age. And then since specs is the effects since diet is the effects variable and age is the moderator, we need to specify a list of values for the moderator age. So I'm saying, let's get the diet effects on hypertension at ages 2, 9, and 16. So if I specify just like this, it'll give me those diet effects expressed in log odds. All right, so at age 2, the control diet, the estimated marginal mean is minus 0.32 log odds of hypertension. All right, so these are all expressed in log odds. Again, that may be hard for you to interpret. So if you want to look at the estimated marginal means as probabilities, I do the same specification as before, but now I add type equals response. These are expressed as probabilities. It's the exact same set of estimates. They're just transformed from log odds to probabilities. Okay, but there's a twist to this, because when I put it in contrast, I can put either one of these in contrast and the results I get out will be different. Okay, so now I'm ready to use contrast to estimate simple effects, right? These are just the estimated marginal means. So a contrast between estimated marginal means is a simple effect. So if I put the first object, which is expressed in log odds, inside of contrast, and I do method equals pairwise and simple equals diet for the effects of diet, I'll get diet effects expressed in log odds. So these, again, are expressed in log odds. You can know it's log odds because you see these negatives, and negatives odds ratios are not possible. So that's one way you can definitely tell. But if you don't put type equals response in the emmeans, you'll get effects expressed on the transform metric. So these are all expressed in log odds. But what we can see here, for example, is that the difference in log odds between the groups seems to be getting bigger with age, right? These numbers are getting larger and larger, or more farther away from zero, perhaps is a better way of saying. That the groups are basically just getting farther and farther apart in terms of log odds of hypertension. But again, some people don't like interpreting log odds coefficients. So if we instead put the emmeans object with type equals response, which expresses them as probabilities, if we put that object inside of contrast, instead we'll get them expressed as odds ratios. So this is the same estimates as here, except these have just been exponentiated now. And so these are the corresponding odds ratios. And you can see it even instead of doing control minus fat, it does control divided by fat. So it's kind of trying to tell you that it's expressing these not as differences anymore, but as ratios. And so it's the same effects, just expressed in a different way. Again, though, an odds ratio of 1 is what represents no difference, basically. And you can see that the estimates of the odds ratios are getting farther and farther from 1 as we increase the age. So basically, we would say that the diet effects gets larger as age increases. Okay. We can also estimate the slopes with EM trends. There's a little difference here, is that there's no direct way to get them expressed as odds ratios. So if I put them in EM trends as I have before, here's the model object. Here is the the variable, the moderator, and then here is the variable whose slopes we want. So these are expressed in log odds. And you can see they look different. But it's hard for some people to kind of interpret log odds or slopes expressed in log odds. As I said, though, there's no real option to get these expressed as odds ratios, so you just have to do it yourself. And the way to do it is stick the EM trends inside of summary and then save that object. That object is basically these columns up till here. To everything to the left is what's inside of EMT. Okay, so everything to the left here. I'm adding 3 more columns where I exponentiate the age trend column, and then the lower limit and the upper limit. And then I get the odds ratio, and then the lower limit for the odds ratio, and the upper limit for the odds ratio. Okay, so it's not hard. You're just going to have to get these odds ratios yourself manually. You want to do it this way. Okay. Yeah. So that's how you get effects slopes estimated as either log odds or odds ratios. Now, there's different kinds of plots also that I've seen, which are much more common in logistic regression and other nonlinear models, which is a forest style plot. And probably many of you have seen these before. Forest plots are actually used a lot in meta-analyses. So these aren't technically forest plots because in a forest plot, each one of these would represent like a different study. So I'm calling it forest style plot. But basically what's plotted is the actual estimate itself. We're not plotting predictions like we did before. We're plotting the actual, like this estimate, this age trend estimate, or this, actually we're going to be plotting these odds ratios estimates. And this is a common way for them to plot. So for example, here, what you do, sorry, let me back up. What you do is you stick contrast inside of plot, and not inside of EMMIP, but inside of plot. And then what's produced is this forest style plot. Since we put the contrast with the object where they're expressed as probabilities, these are going to be odds ratios. So you can see that all of these are positive as odds ratio, well, are non-negative as odds ratios are. Odds ratios cannot be negative. So you can see this is the estimate of the odds ratio itself, and then this is the confidence interval around the odds ratio. And what's interesting here, or the interactions, we can see that the differences between these odds ratios become more and more pronounced as age gets higher and higher, right? So odds ratio of 1 represents no difference. And so oftentimes people add a reference line at 1, which I did with this ggplot coding right here, very simple. And they just add this. So here's an even different way you can visualize the interaction in a logistic regression by this kind of forest plot style. Okay, and again, the only thing you have to do there is put the contrast, which estimates the simple effects as odds ratios, inside of plot. If I had done the other contrast, where the simple effects of diet are expressed as log odds, I would get those estimates, the log odds coefficients with their confidence intervals instead. But most of the time I see these for odds ratios. Okay, but you don't have to graph it like this. It's kind of up to you. You can always go back to your interaction plots that we've been using all before through EMMIP. If, for example, you want to plot them on the log odds scale, our diet effects, we use the EMM object where we did not say type equals response, where all of the estimated marginal means are expressed in log odds. If we use that object, then the predictions will be expressed in log odds as well. So here, this is the object where they're log odds. Age is going to be the break variable, the moderator, and then diet is going to be the X variable here. And so as you can see, we have negative values, which tells us we know this is in log odds. But we can see the interaction very clearly here because all of these are going to be expressed kind of as straight lines. We can also plot our simple slopes with EMMIP. Remember, for slopes, we put the model object first, break variable, x variable. We give it a list of values at which to plot the continuous variables. Here, again, you can see that this is log odds, and now the lines are straight, right? That's to be expected when we plot in the transform metric log odds. Okay, it's nice and easy then to see that the risk of hypertension increases with age in the fat and starch group, but does not increase with age in the control group. Okay, so it's nice and easy to see that. Here we have the plots on the probability scale, and it's not going to make a huge difference in the look of these diet effects. So all we do to plot them on the probability scale is to add type equals response to the EMMIP. Everything else is exactly the same as before. Now you can see that probabilities are being plotted here. And this graph actually doesn't look that different, but the one that will look different is the slopes of age. So on this graph, you can see that we have curves now, and it can again be a little bit harder to determine if these are non-parallel or not. Like, is this blue curve kind of parallel or not with the green curve? It can be hard to tell because in fact, the original two lines are pretty parallel. They're pretty close, whereas here they look less parallel. And so that's what I'm talking about, that it can be a little harder to judge whether there's an interaction on the probability scale if you modeled it on the log odds scale. So things to consider when you have a logistic regression. Okay, the final section, which I'm not going to cover today, is on do it yourself. And I leave this here. I'm just going to tell you that there are ways that you know what, let me back up. First, let me ask, are there any questions on the logistic regression? I should have stopped there, I'm sorry. Are there any questions on the logistic regression section? Basically, you just need to keep in mind that you can express the results in two different metrics usually, and you can graph them in two different metrics. And those choices are up to you. They all have their advantages and disadvantages. Okay, then if there are no other questions, this DIY section will teach you how to do this without emmeans. And it's actually not very difficult. I'm not going to go over this in great detail, but I just want to give you an idea of what's going to happen. As somebody brought up before, remember that these lower order coefficients are they're interpreted as the effect of x, for example, when z equals 0. But what happens if we recenter z to be somewhere else? What if we change the meaning of 0? That's what we're going to do here. And so, for example, if I instead have a variable that's called z star, and z star equals z minus 5, if I then interact x with z star, this coefficient for bx is now interpreted as the effect of x when z star equals 0. But when z star equals 0, that means that z equals 5, right? So we can interpret this coefficient for bx as the effect of x when z equals 5, which is the same as when z star equals 0. So the way we can estimate these other simple effects at other values of the moderator is by recentering z. Or if z is categorical, we can change the reference group, right? So if z is female, right, is a dummy variable for female, where 1 is female and 0 is male, this x variable will be interpreted as the effect of x for males. But if I change the reference group to females, so now z star represents 1 equals male, 0 equals female, then this x coefficient will now be the effect of x for females. So that's all we have to do to estimate the different simple effects is to recenter the z variable, the moderator, or to change the reference group if it's categorical. All right, and you can actually do that quite easily, even without adding any variables to the model. You can, for example, just recenter right in the regression model. So this recenters age at 9, for example, and now these diet effects are the effects of diet when age equals 9, for example. And I can just rerun this model at whatever age I want, and then these will be the simple effects at diet at that specific age. On the other hand, I can also, if I want to get, one thing that's very important, I should say, is that when you recenter the model, the fit of the model is exactly the same. It does not change the fit of the model at all. Or I can recenter a categorical, sorry, I should say changing the reference group of a categorical variable is what I should have said there. So for example, here, this is the age effect for the control group. There is another convenience function called relevel, which I can use to change the reference group of a variable inside of a regression model. So here I'm saying now change the reference group of the diet variable to fat. Okay, so now this age slope is no longer the age slope for the control mouse. It is the age slope for the fat mouse or the fat mice right here, right? So you can, again, if I change this to starch, then this age coefficient would be the coefficient, the slope of age for the starch group. So I can get every estimate I want and every comparison I want by changing reference groups and by recentering. And that's all it takes. So it's really no extra coding, nothing particularly complicated. It's pretty simple. And you can get confidence intervals with confit, for example. And then when you want to graph, what you're going to do is you're going to use predict to predict values. And here I show you how to get predicted values at specific values of your predictors. So this is basically more or less what emmeans is doing under the hood. It's creating this data set of predictor values, then getting predictions for those predicted values using predict. All right. And one of the options, at least for linear models, is you can add the confidence for that prediction. So I can add this set of predictions with their confidence intervals, and then I can add it all to the predictor values that it's associated with, and now I have a data set that's ready to plot. Then I show you basically how I can use that plot data with ggplot to basically recreate those emMIP plots. Right. One nice thing though is that you have full control over how the plot looks if you do it yourself. Right. So these will look very similar to emMIP, but you can also plot these if you don't want to use ggplot. If you like some other, if you like base R plotting, for example, you can do that here easily. Okay, so the one last thing I want to talk about today before we end is extending to three-way interactions. And we don't have a lot of time to talk about three-way interactions, but all I want to say is that you can extend these to three-way interactions in a very straightforward manner. And generally, the only thing you need to do that's different from what we've done before is when you specify specs, you're going to put one more variable in there compared to when we had a two-way interaction. All right, so here I'm modeling a three-way interaction of diet, sex, and age, right? Two categorical variables and a continuous variable on weight. All right, so what's intimidating about these models is how many coefficients are estimated, right? It's a lot to get through. And it's kind of hard to describe this, you know, if you're writing up your results in a manuscript, you don't really want to sit here and interpret every coefficient. Usually you're more interested in expressing the effects of something, right? So that's again where emmeans can really come in handy. So we're going to do it just like we did before, same procedure. So if, for example, if we want the simple effects of diet at each sex across different ages, we're going to use emmeans first, just like we did before. Here's the model object. I put all of the interacting variables inside a spec. So now there's three. This is the difference, is that you just keep adding all the interacting variables in. Since one of them is continuous though, I need to specify the the values of age at which I'm going to estimate my simple effects of diet. So now it's going to give me the simple effects of diet for each sex at each of these three ages. So I have 6 sets of simple effects, right? One for male at age 2, one for female at age 2, and then for the 2 sexes at age 9, and then for the 2 sexes at age 16. So all of these are diet effects, and the three-way interaction allows the diet effects to be different across every one of these sets, right? The diet is allowed to vary by age, by sex, and by sex and age, okay? Now, the real difference, the one thing that might be slightly different is how we're going to use the graphing function emMIP. Now the formula is going to have a third variable. And it's going to be the same as before, where you're going to have break variable tilde x variable, but then there's this pipe And the pipe separates the third variable, which is I'm going to call panel variable. And the panel variable is going to have separate graphs created across the levels of that panel variable. Okay, so if we're interested in expressing the diet effects, again, we'll put diet on the x-axis. We're going to have separate lines and colors by sex. And now I'm going to panel by age. So this is age 2, this is age 9, this is age 16. And then we can see the sex is the separate lines and diet is on the x-axis. And now we can see the three-way interaction. And the three-way interaction basically means that the two-way interaction, for example, of sex and diet, varies across age. So the pattern of these lines, like if all of these look like, if you know the two sets of green and red lines, if they all look like this across the three panels, that would suggest that there is no three-way interaction. But the pattern of the lines is quite different, right? So here they're very close, for example, the red and blue dots, here they're very far away, and here they're kind of in the middle. So the fact that, these lines, the two-way interaction of sex and diet looks different across ages, that is what the three-way interaction means. So it means that the two-way interaction is different across levels of a third variable, all right? And that's depicted here. We can also estimate slopes with EM trends in the same way. So we're putting age as the slope variable. Now we have two moderators, diet and sex. So we'll get six slopes estimated here. Okay, so this is the slope of age for a control male, a slope of age for a fat male. And these are all allowed to be different because we modeled a three-way interaction. Now, though, we may want to put age on our graph on the x-axis since we're visualizing its slope. We'll have separate lines by diet and we'll panel by sex. And again, it's the pattern of the lines that's different between now. Now, like in the left graph, the blue and green lines are basically parallel and the red line is quite different. Whereas on the right panel for females, the blue and green lines look different and the blue and red lines actually look kind of similar in terms of slope. And that is the three-way interaction. The two-way interaction of age and diet varies across the sexes here. And so that is, the three-way interaction. Each of these is, again, graphing actually the same thing. It's just depicted in a different way. And so it's kind of up to you how you want to, assign a variable to be the break variable and to the panel variable. Again, I would suggest that you put the variable whose effects you want to actually visualize on the x-axis. Probably the variable that has fewer values should be the panel variable, and the variable that has more values should be the moderator. Because if you have a lot of values in your panel variable, then the little panels are going to be really, really small. So probably the variable that has fewer values should be the panel. Okay. And that is basically all I'm going to discuss today. I'm going to stop here and say thank you very much. I know that's been a really long ride, a lot of information, but hopefully you got something out of it. Analyzing interactions and visualizing is a very common task for many researchers. So it's really nice that R and the people who made the emmeans package made this package that's very easy to use and quite intuitive, and you can really easily extend it to all kinds of regression models and to three-way or even four-way interactions. It should be able to extend as to higher order interactions as well. And so yeah, thank you again for sitting through this and for doing the exercises with me. I really appreciate it. I had a great time, and come back and come visit us again sometime in our next set of workshops in the spring. Okay. All right, I'm gonna stop the recording. Oops, no, that's stopping sharing. Hold on, let me stop the recording.